In the last lecture, we started the discussion of a method which is called analysis of variance, and as I promised, this method is also widely used. It's very popular, and we will see this method in econometrics classes, and today we will have some extension of this method. Well, the idea is that with the help of ANOVA, we are able to compare several means of the data for different populations. So we split all our observations according to some qualitative criterion. In our example, it was different oil wells, and the numerical or quantitative measure was the daily extraction in tons. Yeah, so the idea was to represent each observation, so the quantitative measure or our variable, as the sum of three elements. So one is the overall mean, like you just believe that any oil well in the world is able to produce some mean value of oil. So then there is an effect of treatment, depending on the technology you use, maybe depending on the place where you make this extraction. There is a different effect. And the third part is a random error. So the random error represents all other factors that can also influence our variable. And overall, our model is additive model which consists of three parts. One part overall mean, mu, another part is the effect of treatment, and the third part is the random error. And according to this model, we understand that mu is constant, so it cannot cause any kind of variation in xij, right? So mu is always the same. Therefore, xij can change because of two different reasons, due to two different reasons. So one reason is change in alpha I, and another is changing this epsilon ij. And we call the first part between variation, so the variation between different groups of data, or between different treatments, or between different populations. And the second source of variation is this random error, which is thought as the result of other factors which are not represented by the treatment. So epsilon ij, and we call this within variation. And the ANOVA is established as the comparison of these measures of variation, which are called sum of squares. So we take the total variation in x in our sample, and we measure this with the help of sum of squares total, and this variation in alpha, is represented with sum of squares between, and variation in epsilon is represented with the help of sum of squares within. So then we compare these two parts, and if sum of squares between is significantly greater than sum squared within, then we conclude that different level of treatment, or different populations, or different groups, they have different population means. So formally, we tested this hypothesis, the hypothesis that several population means are equal. So mean mu1, mu2, up to mu_k. And the alternative hypothesis is that means are not equal for some particular pair of groups, I and I prime. We use this type of test statistic. K is the number of groups, and n is the overall number of observations for all groups. And we are familiar to F statistic. We used F statistic in previous topic when we compared two different population variances. So we just take a critical value of F statistic, but we want to be sure that SS between is greater than SSW. So therefore we test this as the right tail hypothesis, only one-sided. So we want F to exceed the critical value from the right. So therefore we take the upper quantile of F distribution, so never take lower quantile, it's not reasonable, and compare the given statistic with this. And on the other, so the other way how we can calculate this F statistic is to rewrite the numerator as mean squared between and denominator as mean square within. So this is, you divide the sum of squares by the degrees of freedom, you have something which is called mean square. So here is an example that we used in the last lecture, just as a reminder, because we will continue working with this example. So we had 4 oil wells, we have 10 days of observations, we recorded the daily extraction of oil for each oil well, and our task was to test if a particular well has significantly different productivity compared to other wells, or maybe several of them. So we wanted to apply that ANOVA test. So here is the result. We calculated sum of squares between, we calculated sum of squares within. Also, those are called wells and error. So this is the reason why X changes due to wells. And this is the reason why production of oil or extraction changes due to the error term, to the epsilon. And so F statistic was here, 10.9. We found the critical value of F statistic, which is 2.87, and the rejection region in this case is here. So we see that F falls into the rejection region, therefore we reject the null hypothesis.
Sorry, error is within, right?
Error is within, yes.
Okay.
Well, we concluded that there is a significant difference in daily oil extraction for the observed 4 oil wells, but we still don't know which well is better or which well is worse. So we are not sure about the particular group which differs from others, or maybe there are several groups that differs from others. Well, it has, so now we start the today's material. The application of this F test has unsatisfactory result. So we know that the means are different, they are not equal, but the test gives no information about how they differ. So we just concluded that among 4 oil wells, there are some oil wells that differ in terms of oil extraction, mean daily oil extraction. That's it. So which pairs are significantly different? Well, the naive approach, which is familiar to us, would be to compare all pairs of treatment means using t-tests, right? So we know what is t-test. T-test helps us to compare 2 samples. So you can suggest, why can't we take, going back to the data, why can't we take well 1 and well 2 and compare them? Then we take well 1 and well 3 and compare them. Then we take well 1 and well 4 and so on. So that's a reasonable approach, right? So just take 2 wells and make pairwise comparison for each of them. We know how to do this. The problem is that we have somehow related observations. And the problem is that once we want to test the hypothesis, this pairwise hypothesis about the population means for each pair of wells, this approach will have the following problem. So each individual comparison will have a type 1 error rate of alpha. That's okay. So we will apply alpha as the size of a critical region or as the size of a type 1 error, and we will use this. But the problem is that overall together, because look, we are talking about related hypotheses. So overall, the collection of all these comparisons would not have the type 1 error equals to alpha. I'm not going to discuss this statement here, so try to believe me, but we will discuss this in econometrics, and that topic is going to be called joint hypothesis. So once again, the problem is that this is not a single hypothesis. If you would have well 1 and well 2, that's totally fine. We can compare these two wells, no problem. But we have well 1, well 2, well 3. And when we compare means of well 1 and well 2, and then well 1 and well 3, these two hypotheses are gonna be related because we are not sure about population mean of well 1, and we don't know about the population mean of well 2 and well 3. So given that well 1 has its own confidence interval, the difference between productivity of well 1 and well 2 will have also some confidence interval, and this is also related to the third well, because third well is also related to the second well, and therefore we are in trouble. So we have some circle of these hypotheses and they are related, right? And this is called the joint hypothesis, and we really want to be careful about this. And as I promise, in econometrics we will discuss this issue, so more, let's say, in a more formal way. But one thing you must remember: once you have several samples and once you have several estimates based on this sample, and if you want to apply the hypothesis about some parameters of these samples, and if these hypotheses are related to each other, then you cannot use these simple tests. They are not reliable. You must come up with some more sophisticated approach. That's because formally the probability of a type 1 error will be different and significantly larger than usual.
Really? Why is it alpha? Like it is another alpha, not like significance level.
It's significance level.
But is it?
So significance level has several other synonyms: type 1 error, probability of type 1 error, right?
Okay.
Or size of a rejection region, or size of a critical region. So there are many different
False
synonyms.
negative. Yes. Okay.
Yes. Yes. Yes.
Okay. Okay.
So how we can solve this? So there are two different approaches. So one is the most popular approach, is called Tukey's method. Another one is Bonferonni method. As I said, the most popular approach is the first one. So we will pay more attention to the first approach, and the second approach, I just briefly mentioned how it works. It's simple, but, well, for example, in statistical software, the first approach is used in most of the cases, and the second approach is rarely used. So what is the idea of these Tukey's methods? Once again, so we came to the point when mathematics becomes, well, very sophisticated. So that is why, as much as I can, I'm trying to avoid all these derivations, because probably you will never use them. So I just want to give you an idea of this method. So we want to construct confidence intervals for the differences of all pairs of means, such that all these confidence intervals have the same confidence level, let's say 95%. As I said, if one confidence interval for the difference between extraction and well 1 and well 2 is is established, this confidence interval will depend on the confidence interval of the difference between well 2 and well 3, and they all are related. So therefore, we want jointly to establish these confidence intervals such that all of them simultaneously have 95% confidence level. So the confidence intervals must simultaneously have a set coverage probability, like 95 and 99%. I hope you remember that confidence intervals are somehow related to the hypothesis tests. Once we have 95% confidence level, and once our hypothesized parameter value is outside of this confidence interval, then we reject the hypothesis, right? Because it falls into the rejection region. So basically, the rejection region is everything that is outside of the confidence interval. Therefore, once we build these confidence intervals for all these pairs, we can transform this approach into the hypothesis test. So, as I said, I omit all the mathematical details, how we derive those confidence intervals, how we derive the statistical test, only the most important things, how you can operate with this method. So here is a test statistic. You see, it looks very similar to what? It looks similar to t-statistic, yes. The only difference is that in the numerator we have absolute value, and in the denominator we have this ni. So I was a little bit troubled with this with the notation here. So I've chosen one type of notation, but basically, so probably I needed to change it. So what is ni is this. So how many observations in one column you have. So here. And for this Tukey's method, we need to have equal sizes of columns. So therefore, this n is going to be the same for ni and for I and I prime. This is going to be the same. So therefore, this notation is a little bit slow, and that's why probably I will rework this later on. But ni is the size of this column, and we believe that this column must be equal for I and for I prime. So Tukey's method is applied only for equal sizes of every column. So xi bar, xi prime bar are sample means for groups I and I prime. SP is pooled standard deviation, and we can calculate this as a square root of a mean square within, which is here. So this is a sum of squares within divided by n minus k. So basically, this is the standard deviation of an error term. And this test statistic, so it's not t, but it looks similar to t. Therefore, it has a studentized range distribution. So it's not a student's distribution, it's another type of distribution. You see that this distribution is always positive because this variable is always positive. So the absolute value in the numerator never gives you a negative number. The operations with this distribution are exactly the same as usual. So I mean that you just need to understand, so there is a variable that has some special distribution. It's not student, it's not f, it's not chi-square, it's not normal, it's just some other type of distribution. So if you want, we can have a look how this distribution looks like. Studentized range distribution. Well, yeah, it's here. You see that this distribution for different degrees of freedom, it always positive, and it looks like, well, weird thing. Basically, for different degrees of freedom, for small degrees of freedom, it looks like this half of bell, and then when the number of degrees of freedom increases, we have these skewed bells and so on. As I said, this is just another type of a distribution, but we work with this distribution in a usual way. And what is this usual way? We want to find the critical or rejection region for this test statistic based on this studentized range distribution. And there are two parameters, k, which is the number of samples being compared, right? So this k, how many groups do we have when perform ANOVA, and n minus k. N minus k is the number of degrees of freedom for SP. So it's visible here. So this is k, one parameter, and another parameter is degrees of freedom. And depending on them, as I said, the shape is kind of different. So, formally, how do we perform this test? We perform this test for every pair of groups. In our example, it's every pair of oil wells, well 1, well 2, well 1, well 3, well 1, well 4, 2, 3, 2, 4, and 3, 4. So overall, like there are six different comparisons, and also we can compare them in the reverse way, 4, 1, 4, 2, 4, 3, and so on. So 12. For every pair where I is not equal to I prime, the null hypothesis is going to be that means for both groups are equal. And for every pair, the alternative hypothesis is going to be that means are not equal. So now we do this pairwise comparison, but not with the help of t-test, but with the help of another test, which is called Tukey test. The test statistic is defined, and the critical region is the following. So this test statistic, since this is the positive value, it must also fall into the right tail of the distribution. So therefore we take only right, the upper quantile of this test statistic. So 1 minus alpha, k is the first parameter, n minus k is the second parameter. So k is the number of groups that we compare, n minus k is the difference of the number of degrees of freedom for student for the pooled standard error, for the pooled standard deviation, sorry. And this is the same as the denominator here, n minus k. So yes, it's 1 minus alpha quantile of a studentized range distribution. In Python, we apply the following function. It's the same as usual. We take the library stats, we take function ppf, but now we write the name of a distribution here, studentized underscore range. We provide the number, the value of quantile 1 minus alpha, so k the first parameter, and n minus k the second parameter. So we see that everything is familiar to you. We are doing this already 1.5 months, or maybe even more, 2 months. And all the time when you test the hypothesis, all the time that you calculate the quantile, you use the same function. Now there is just another distribution that you need to call for. A simpler way, if you rearrange this inequality, when we multiply this quantile by sp divided by n by the square root of n, we will get this. And why it is simple? Because now we can compare just this difference in sample averages or sample means with some number. And if this average, if this difference in averages exceeds a given number, then we reject the null hypothesis. And we conclude that population means of two groups are not equal. So you can use this, but usually for practical purposes, the second inequality is just simpler because, well, as I said, you need to compare the difference in sample means with a given number. So back to our example. Now let's go through all these steps for the test. So basically one new thing for you. One new thing is this new type of distribution that is used in order to obtain this critical value or quantile. All the other things are more or less familiar, and the whole algorithm is also similar to what we did in many previous lectures. So what do we know? We know this sample means for every oil well. So we know that the sample mean for the extraction for the first well is that much tons, for the second here, for the third here, for the fourth here. We know that overall we have 40 observations, 10 for each group, and the number of groups k is 4. So this is the overall number of observations. Please be careful. So n is how many observations in total we have. So we also calculated sum of squares within here, and we know how much is mean square within this. So now the pooled standard deviation is the square root of mean square within, and this is 0.1192. When we apply that function in Python, we have Q, or the upper quantile of the studentized range distribution, equal to 3.81 around. Now, so I decided to use the second inequality when we take this quantile, multiply by the standard error, right? So the pooled standard deviation divided by square root of n, which is here, and we have 0.1436. So what is this number? Back to the previous slide. If the difference between two group averages exceeds in the absolute value this number, 0.1436, then we conclude that these two oil wells produce different amount of oil. Otherwise, we cannot conclude that two wells are different in terms of their daily production. So we need to make pairwise comparisons. So first, we compare the first well and the second well. We do this. We calculate the absolute value of averages for the first well and average for the second well. We have this value, we have 0.078. Now we compare this difference with the given critical value. Well, 0.078 is less than 0.1436, so we cannot reject H null. The means are equal. This part is exactly same as we used in any other hypothesis test. Calculate statistic, compare this with the critical value. If this statistic falls into the rejection region, which is defined in the previous slide, then you reject the null hypothesis. Otherwise, as in our case, we cannot reject it. So the next pair, 1 and 3, here. The difference is 0, 2, 3, 7, and we see that this difference is greater than the critical value. So in this case, we reject the null hypothesis and we conclude that the means are not equal. Now we can conclude that the mean production of oil, or average production of oil, in the third well is significantly less than in the first well. So we see the direction of difference, right? So this is less than this. So the third well significantly differs or worse than the first one. And we continue doing this for every pair. So pair 1 and 4 here. Difference is 0.047, less than the critical value, cannot reject H null. The means are equal. Then we compare 2 and 3 here. So the difference slightly exceeds the critical value, but still we reject H null. The means are not equal. So now we can conclude that val 2 performs better than val 3. So now we know even more. Now we know that val 1 and val 2 do not differ, right? So it's here. But we also know that val 1 and val 2 both produce more oil than val 3. That's why these hypotheses are related to each other. That's why we posed that trouble in the beginning with this pairwise comparison. So while comparing x2 and x4, we see that this difference is not does not exceed the critical value, so we cannot reject H null. The means are equal, so 2 is not better than 4. And finally, we compare number 3 and number 4 here. Well, the absolute value of this difference is 0.284, which is greater than the critical value. So again, we reject the null hypothesis. The means are not equal. So overall conclusion is that we identified that oils vals 1, 2, and 4 are not different from each other in terms of their mean production of oil, while val 3 differs, and this pairwise comparison showed us that val 3 is less productive than the other oil wells. That's simple. So we start with ANOVA, and with the help of ANOVA, we conclude that means are not equal. And while we have this result, while we reject the null hypothesis in ANOVA, we come to the Tukey test. We perform this Tukey test, and we see that which group exactly differs from other groups. In this case, only one group is different, but in principle, you may have several groups that are going to be different from other groups.
Sorry, why do you say that if one is more than other? If like, do we state that they are just different, or we already state that one is more than other?
Well, your question is fair enough, right? So our alternative hypothesis is not equal. To be more precise, so we may write that those are greater. But once you say that they are not equal, it means that it's either greater or less than, right? So still not equal means one of these two directions. And I doubt that if you have sample average 3, 8, and sample average for 0, that population mean of this can be greater than population mean of this, right? So basically, once you reject the null hypothesis of mean equality, you can look at how these sample means are related to each other, and well, you conclude that, well, the population mean of the first well is greater than population mean of the second well. Why? Because first fact, you rejected their equality, and when you rejected their equality, it is not possible that the population mean of the third well can be greater than the population mean of the first well, because in this case the random sample means can coincide.
Okay, I was just worried about the last example of comparison third and fourth one. Yes, and so in the last example,
This one,
fourth one.
you see that it's 3 minus 4. So the third is less than fourth, right?
Yeah,
Because we rejected the null hypothesis, the means are not equal, and we see that the third is less than fourth. So as I
okay,
said, wells 1, 2, and 4 produce more oil than well 3.
okay, that's great. Thank you. Understandable.
Uh, just one additional thing. So in most of the times, people are confused with this alternative hypothesis. Uh, so usually, in most of the cases, we state this alternative hypothesis as not equal. In rare cases, we want to be sure about the direction of this inequality. Either it's less than or greater than. Or sometimes it's even only one reasonable way to think about this. So for example, when we perform this f-test, uh, and when we compare numerator with the denominator, basically we compare something like the population variances of this and this, even though we formulate the alternative hypothesis as not equal, as means are not equal. But we test something related to variances, because this test is about variances, it's not about means. And we want this variance to be significantly larger than this variance. Why do we want this? Because we want the variation coming from alpha to be large enough in order to conclude that this variation matters. So therefore, this is one-sided test. And therefore, we formulate the rejection region only as the right tail, not left one. In this case, we also formulate the rejection region as the right tail of the distribution. In this case, this formulation is due to the fact that we take absolute values. So the absolute value, well, definitely, if it's close to 0 to the left tail of this distribution, and once again, let me show you that this distribution, the left tail of this distribution ends at 0. So there is no chance to have your test statistic less than 0. So therefore, it's not reasonable to take the left-sided confidence interval, or like half of not confidence interval, the rejection region, left tail. It's not necessary to take. Why? Because it is just unreasonable. So you want this difference, either it's negative or positive, but the absolute value of difference large enough. So therefore, we take only the right-sided tail. Something like this. Usually, if there is a need for one-sided alternative, your question is gonna be something like, well, do we have enough evidence that something is less than something? Or do we have enough evidence that something is greater than something? In this case, you directly you are directly sent to a particular type of alternative. If there is just, do we have an evidence that some population parameter differs from some number or from something else, then you state an alternative hypothesis as not equal. And that's it. So that's, let's say, a practical approach, right? How to deal with all these things. So don't be confused. It's kind of a simple thing. But it came to my mind that probably I need to make some short tutorial for you how to deal with this, how to formulate null hypothesis, alternative hypothesis in different cases, and what is the like step 1, step 2, step 3. So probably I will do this in a free time. So you see that this procedure is kind of time consuming. So we need to repeat all the things again and again and again. A lot of computations, even though there are simple computations, but still a lot of annoying things. So that's why we prefer, in this case already, we prefer to do some coding and to allow, let's say, Python to calculate this. So I'm not gonna show you right now how to do this, but I will record the tutorial how to get the same results with the help of Python. There are just like two commands, and you will get something like this. So you'll get, so this is exactly the test for the those 4 oil wells performed by Python. So you see that it compares as usual. It is not well 1, well 2, well 3, well 4. So as usual, Python counts everything from 0. So therefore, 0, 1 means we compare well 1 with well 2. Statistic 0.078. Let's compare this as what we have calculated. It's here, right? So 0.078. It calculated us the correct result. But now, instead of this Q and instead of critical value, we have p-values. And as we discussed, p-values are also very nice and convenient way to test the hypothesis. Once p-value is small, once p-value is less than alpha, we reject null hypothesis. In this case, p-value is 47%. What does this mean? It means that if we believe that population means are equal, population means of production in well 1 and well 2 are equal, then the probability to obtain this difference is 47%, which is okay, right? So it's large probability, so we cannot reject null hypothesis. But in the next step, when we compare well 1 and well 3, if we believe that both wells produce the same amount of oil, the probability to obtain this sample difference is, well, it's almost 0. It's not 0, but it's a very small number, less than 1,000, let's say, which means that it's very low probability to obtain this difference, 237, right? So it's here. Given our belief that 2 population means are equal, what do we conclude? If this probability is very low, then probably our belief is false. Null hypothesis is not true. We reject this null hypothesis. The same conclusion as on the previous slide. And moreover, your decision is supported by the 95% confidence interval. Look at the lower confidence level, upper confidence level. You see that 0 falls into this confidence interval, into the first one. What does this mean? If 0 is there, then there is a high chance that there is no difference between mean productivity of the first and second wells. While in the pair well 1 and well 3, 0 does not fall into the confidence interval. What we conclude, with 95% chance, this difference is not 0. Well, we are totally fine with such confidence to reject the null hypothesis and to claim that, well, the third well performs worse than this first well. And we do this for every pair. You see that there is much more than 6 pairs, because there is 0, 1, and there is also reverse 1, 0. And the difference is given the same, but with the negative number. But as you see that the p-value is the same. Basically, there is no difference whether you take this or this. And
But
maybe what?
Sorry, but when p-value exceeds, like, it is 0.8, is it just a percentage?
It's
Or
47%, yes. 47% or 81%. And as we discussed in our introduction to hypothesis testing, p-value is the probability that you obtain this sample given that the null hypothesis is true. So if I believe that null hypothesis is true, the probability to obtain this result is almost 0. So what is my conclusion? My conclusion is either I'm a very lucky person, so lucky that I have the realization of this small chance, or, which is more reasonable to assume, that my null hypothesis is not true.
okay.
So p-value usually is much simpler. You don't need to calculate the critical value. You just look at the p-value. You know that p-value is always normalized. It's always from 0 to 1, because this is a probability. And the less is the p-value, the higher the chance is to reject the null hypothesis. So basically, you want to reject the null hypothesis when p-value is less than 5% or maybe 1%. It's much simpler.
Okay.
So basing your decision on p-value is much simpler than calculating the critical value. But sometimes critical values needed to be calculated because p-value is not available, for example, or maybe I ask you to calculate the critical value and make this test based on the critical value instead of p-value. But with our progress to the further topics, we will switch to p-values more and more, and we will rely on them more.
So in the third example, when p-value is 81%, it means that there is a high chance to get this statistic when H null is true.
Yes, so 81% that H null is true, and you obtain this difference.
So, and if exceeds alpha, that means that H null is true, right?
No, it should be less than alpha.
Should be less than alpha.
In order to reject null hypothesis. If it's greater than alpha, you cannot reject null hypothesis. So let me remind you from lecture.
I remember, but I just can't get it.
So it was here.
Like, can we discuss it after the lecture? Also, I have a question, like, about
sure.
So now let's just go on, I guess.
Sure, it was here. Yes, so we discussed it here. So p-value is observed significance level. So the smallest level of significance for which the observed data indicated an null hypothesis should be rejected. So basically, we compare this with alpha and reject if p-value is less than alpha. Okay, so this is the output of Python regarding Tukey test, and another approach, as I said, which is less popular, but also sometimes, for example, you do not have an access to Python. I don't know, in the field, you need to compare the productivity of oil wells, and you do not know how to deal with this queue, how to calculate this properly. Well, then we can obtain Bonferonni method. It's less rigorous, less strict, but still works. So if we test our null hypothesis, so some number of our null hypotheses, a desired type 1 error rate of at most alpha can be guaranteed if we use t-test for two sample means at the level alpha over r. So what does this mean? It means that we can do the same as before. We can compare these sample averages pairwise with the help of t-test. But for the t-tests, we need to use alpha over r significance level. It's not alpha, it's not 5%, let's say. It must be 5% divided by the number of hypotheses that we test. And we are gonna be fine with this. Again, it's crude, it's not exact, but as a rule of thumb, as some kind of simplification, it's possible to do. So the test statistic is the familiar t-statistic from the two sample hypotheses. We have difference in sample means divided by the pooled standard deviation multiplied by this square root of 1 over n1 plus 1 over n2. So must be I and I prime. Yeah, must be ni and I prime. Just, you know, to have it the same. Yeah, it's simple, versatile, and gives good results if R is not too large. Once again, it's not rigorous. So Tukey test is a proper test. It's mathematically, formally proven. Everything is fine. And that's why in the software, we usually use this. But if for some reason you do not have software and you need to do this pairwise comparison, you can go with Bonferonni method and this test statistic. So how to apply this to our example? We have 6 pairwise comparisons to be made. So this is the binomial. So this is the number of what? Combinations. I hope you remember somehow the probability course and the counting. Oh, it was lecture number 4, I guess. So 6 pairwise comparisons. So those are here. 1, 2, 3, 4, 5, 6. So if we take, let's say, alpha of 5%, alpha over r is going to be approximately equal to 0.83%. Now we take a critical value of a t-statistic, right-tailed upper quantile of this 1 minus alpha over 2 and 36 degrees of freedom. Why 36? Because we apply the same number of degrees of freedom as this SP has in the denominator. So SP is known. We have calculated this earlier. And now, just for example, how do we perform this? It's a usual t-test for 2 samples. We take first mean, second sample mean, pooled standard deviation, multiply by the square root of 1 over 10. So this is the column 1 size, 1 over 10 column 2 size. And we have t equals 146. Critical value is 279, so we cannot reject the null hypothesis, means are equal. If we take the pair of well 1 and well 3, t statistic is 445 almost. So there is just a difference in the numerator, denominator is the same. And in this case, t statistic falls into the rejection region, so we reject the null, and the means are not equal. So I decided not to do this for all pairs, but you see that at least for these two pairs, the result is exactly the same as the previous method. So it's simple. We can use the familiar method from the two sample hypothesis tests. And one more thing, why this approach can work. As I said, when we applied Tukey's method, for this method, we want steps. Yeah, okay. So for this method, we want all columns to be equal. So we want the same number of observations for each sample. Because here this pooled variance is calculated based on this approach. And also here, look, when we calculate the test statistic, we divide by n I, and this ni must be the same as ni prime. So basically this must be the same number. And this is the weakness of Tukey's method. If you have an equal number of observations for each sample, you can go with this Bonferonni method, because in this case you see that you have sizes of both samples, of sample 1 and sample 2. And in this case, it gives you more flexibility to apply this approach to some other cases. Yeah, so with this, we finish the topic about one-way ANOVA. So one-way ANOVA was about comparison of population means for different samples, and these different samples are having different levels of treatment or some other qualitative differences. Those may be, like in this example, different technologies used to extract oil, different levels of drug, different amount of time spent with the home assignments, and as a result, like different, let's say, grades obtained in statistics scores. So anything. So the idea is that every group somehow qualitatively differs from the other group, qualitatively differs from the other group. And the logical question is, what if we have another factor that also can affect the outcome of this experiment? So in this example that we have studied, we assume that only technology affects the extraction of oil, and there is some other factors that are hidden in the error term. But the question is, what if there is some other qualitative factor that can additionally make changes in the oil extraction? In this case, we can apply the extended version of ANOVA, which is called the two-way layout. So the two-way layout has almost the same idea, but we have two factors, and every factor must have at least two levels of influence. So, as an example from biology, the levels of one factor might be various drugs, and the levels of the other factor might be genders. So how different drugs are effective on different genders, males and females. Something like that. So here in this topic, in two-way layout, I decided to change the notation, so please don't be confused. This is fully my mistake. I needed to do this kind of somehow homogeneous with the previous topic. But I tried, and well, it was a disaster. So therefore, I decided to change the notation slightly. Don't be confused. So we assume that there are capital I levels of one factor. So regarding our example, we have 4 different technologies applied on 4 different oil wells. J of the other factor. So we have some other factor that has J different levels. And therefore, there are I times J combinations. So let me jump here to the explanation of the example that we are going to use here. So suppose that we have 4 different technologies of an oil extraction. So 4 different oil wells. But also there are 3 different maintenance teams. So workers, teams of workers who kind of make a maintenance or service of those oil wells. And they are rotating around these oil wells. And they can also influence the production of oil. So we have J equals 3, and those 3 different teams are 3 different levels of the second factor. So, and we have assumed that we have capital K independent observations which are taken for each of these combinations. So what does this mean? Look, we have let's say we have well number 1, and there is a first maintenance team working for 10 days. And we record every day how much this well with this first team produces. So K is gonna be 10. Then this team goes to another oil well number 2. And for this well, the other team comes, team number 2. And we record 10 days of oil production of a well number 1 serviced by team number 2. Then this team goes, team number 3 comes, and we record the production of well 1 under team 3 for 10 other days. And we do this for all possible combinations, right? So we have 10 days of record for one well and for one team. So overall we have 12 combinations, and for all of these combinations, for each of these combinations, we must record 10 days of an oil production. So overall we will have 1,200 numbers representing the production of every oil well. So there are 12 combinations of these 2 factors, and if we record 10 days of oil extraction for each this interaction, well times team combination, we will get 1,200 observations in total. So suppose that you do this recording in the journal, like, I don't know, you have some journal and every day you record, so well number 1, team number 1, they produced that much tons of oil. Well number 2, team number 2, they produce that much oil, and so on. And you do this for 10 days for every combination. You will get something like the following table, the following journal. So day, well, team, and value, like the extraction. So day 1, well 1, team 1, that much. Day 1, well 2, team 1, that much, and so on. So well 3, team 1, blah blah blah. Then the second day, well 1, team 1, so on. Well 2, team 1. And you do this for 10 days for team 1. So team 1 needs to work in all 4 wells for 10 days, and you record the performance of every combination for 10 days. Then you switch to the second team. Well 1, second team that much, well 2, second team that much, and so on. Then you do these recordings. So of course I cannot show you the whole table of 1200 observations, but I hope you understand the logic of this. Is this clear what is going on?
So every team for every factor for every well
For 10 days. Yes. So basically the most the most difficult thing is to understand how many observations overall do we need, but it's simple, right? So
it will
if
be just the
you have
combination.
no, it's even
Oh,
simpler.
oh.
Look, if you have 4 wells, if you have 3 teams, so you have 12 12 combinations, and then for each combination you need to have several observations, let's say 10 observations, and overall you have 1200. So there are no combinations, nothing. It's just simple application of the multiplication principle.
Yeah, we had it in our probability course.
Yes, multiplication principle. Yes, exactly. So now look, this table is not very nice because, as I said, it's huge and it's difficult to comprehend. What can we do? We can make it look nicer, like this. So what do we have in this table? So we formed something which is called sometimes pivot table. I will also tell you how to work with this table. Where on the columns we have teams, on the rows we have oil wells, and as the values we have average or mean oil extraction for every combination. So this is the average production for over 10 days of the well number 1 under team 1 maintenance. This is the average daily extraction or production of a well 1 under team 2 maintenance, and so on. So those numbers here inside the table are averages. And of course it's much simpler to look at this table and to understand what's happening, because once you look at this, you understand nothing. And this is another task when you do some data analysis. So the task is to represent the data in the most convenient way in order to for the user to understand what's going on. So when we look at this, what we can find out? We can find out, first of all, that there is probably something wrong with team number 2, because the production of all wells falls when team number 2 is there. But this is our hypothesis right now, right? So we cannot claim that, well, there is a significant difference and team 2 is significantly different. Well, maybe not. Maybe this is by chance, because we also have team number 3, which is slightly larger than gives the slightly larger production than others. If you look by rows, do we see something interesting regarding the oil wells? Well, oil 4 has higher productivity, right? Because here we see that, well, on average, okay, but this team number 2, no, team number 2 and well number 2 has higher production. So at least somehow we can get some ideas of what's going on in the data, and maybe there is something wrong with team number 2. So what do we have here? This x bar dot j, x bar I dot. Those are averages for well 1, well 2, well 3, well 4 for I, right? So we denoted with I the oil wells. And those are averages for team 1, team 2, and team 3. So be careful, those are not totals, those are averages over one factor levels and over the other factor levels. And we see that, yes, well, 4 on average produces more than others, while team 2 on average gives the lower productivity. But again, those are random observations, those are random numbers. Therefore, we cannot rely only on the comparison of these numbers. We want to rigorously test the hypothesis that different technology and now the second factor, different maintenance team, lead separately or together to the different productivity. Well, as for the one-way layout, we need to formulate the statistical model for the two-way layout. It's gonna be a bit sophisticated, and we are not gonna do the manual computations. This is, let's say, the good news, because the manual computations are gonna be, well, they are possible, of course. People are doing them, but it's too long. So we will rely on the statistical software output. But still, we need to understand the model, at least what's going on there. So if you remember the first model, one-way layout, when we decomposed every number into 3 parts. Now we decompose every number into 5 parts. Here they are. So the first part is the same. So first of all, we have x, I, j, k. I is oil well in our example, j is the team, and k is the day of the observation. So mu is the overall mean. That's totally fine. Alpha I is also familiar to us. This is the level of production which is attributed to the difference in technology, right? So this is a non-random effect of the level I of a factor 1. So ith well gives us some difference in the terms of productivity. Now we introduce the non-random effect of the other factor, beta j. Here, beta j is the non-random effect of the level j of a factor 2. So basically, this is the effect of a given maintenance team working on the oil well. Well, and there is also one additional factor. We will discuss this issue in econometrics course as well. Try to understand this. Probably, and it may happen in real life, one team is somehow better in maintenance of a particular technology. So, well, maybe they know better this technology and they are able to perform better in this particular technology. Therefore, we need to capture this effect as well, that a given team works better in a given oil well. And this is called an interaction term. An interaction term between level I of a factor 1 and the level j of a factor 2. So as I said, in real life, this means the following. So this means that a particular technology works better. This means that a particular team works better. But this means that a particular team knows better a particular technology, and together they produce better or maybe worse, depending on the sign of this effect. So this is called an interaction term. So a given level of one factor together with a given level of the second factor gives us some additional result, or let's say additional, or maybe not, or maybe otherwise some negative result, depending on the sign. And epsilon is familiar thing. That's an error. That's an error. And we also put some restrictions. Alphas must sum up to 0. Betas must sum up to zeros. Deltas, when we sum them over I, or when we sum them over j, they also must equal to 0. And epsilon is the random term. So look, now, if you got the logic of one-way ANOVA, now we want to capture how much of the variation in x comes from alpha, how much of the variation comes from beta, how much of the variation comes from this interaction, and how much of the variation comes from this random error. So we are gonna divide sum of squares total into 4 parts. And here we are. So first of all, yeah, before this, let's discuss how we are gonna get the estimators of these parameters. So the sample estimate of mu is just overall sample average, x bar. Sample estimate of alpha hat I is gonna be, of alpha, sample estimator of alpha is gonna be x bar I minus x bar. So the additional effect of ith level of a factor 1. So beta j hat is the difference in jth average minus x bar. So the interaction term is calculated in this way. So this is the average ij, which is this number, x bar ij, is taken from that table, this table, from this table. This is xij average. So this is average of xy1, 1, 1. This is average of x1, 2. This is average of x3, 2, and so on. So though we are talking about these numbers. And yeah, so this is how you can estimate this delta. So you see that things are getting not very nice and a little bit complicated. So similar to one-way ANOVA, we do this test based on the decomposition of the sum of squares total. So in this case, we decompose this in sum of squares caused by the first factor, sum of squares caused by the second factor, sum of squares caused by the interaction, and sum of squares error. So there is nothing like within or between right now, right? So there is just, well, we can think about this as the sum of squares within, and all of them are between, but better to denote them as factor 1, factor 2, and the interaction. So the calculation looks like this. So let me skip this part. We will not calculate this manually. Those calculations are similar to one-way ANOVA, but it will take, well, some time to calculate all these things. Well, as I said, in principle it's possible, but it's too long. So here we need to take 12 numbers, here we need to take 3 numbers, 4 numbers, and here we need to take all the 1200 numbers to calculate it. Of course, manually it's not possible. With the help of software it's possible, but basically we can get the following output with the help of Python, for example. I hope you remember that table from the one-way ANOVA. So now for the two-way layout, we are able to establish the same table. Now, instead of val and error, We have val, one factor, team, the other factor, their interaction, val times team, and the error term. So degrees of freedom are given here. Sum of squares are given here. Mean squares. So as before, how to calculate mean squared is just the fraction of sum of squares and degrees of freedom. So for instance, just for example, if we have this 2.22 divided by 3, so we have this mean square. If we have this sum of squares, 5835 divided by 2, so we have this mean square, and so on. So that's simple. But look, now we have 3 f values instead of 1. For every factor that we want to test, we have its own f value. And f value is calculated in the same way. We take mean squared this of this factor and divide by the error, mean squared error. So 0.34 divided by 0, how much? 63. So we have 117 here. Or we have 2918 divided by 0.63. So we have this mean f value here. So at least you need to understand how to get these f values. So you will never calculate these mean squares by your hand, but f values are needed to be known, how to calculate them. And here I decided to put p-values instead of f criticals. So for every of these f values, we must have its own f critical because degrees of freedom are different. But instead of this, we can use p-values. And look, what do we have? We have p-value for val is 0.32. P-value for team, it's like 4.4 or 4.399 times 10 to the power of minus 20. So it's like 0.2004. It's a very small number, almost 0. And this one is 0.56. So what can we conclude about the significance of these factors and their influence on the production of foil? Well, does not have a significant impact on the level of oil extraction. So we can conclude this based on p-value. P-value is larger than 0.05. We can do this the same based on f value. As I said, no difference, but if we have p-value, we are fine. We don't need to calculate the critical f value. So what we can conclude about team? So team has a significant impact on the level of oil extraction. So team, and now we can go back to that table and look at the results and conclude that, well, yes, different teams can lead to different production or productivity of wells. And the interaction term also doesn't give us a significant effect, so we do not believe that a particular team works better on the particular technology. No evidence in favor of this hypothesis. So now we see that we get much richer information about the factors that can affect the outcome variable. And as I said, you can apply this method for any situation when you have two different qualitative factors that can influence one quantitative variable. Like
So here we, sorry, here we don't compare like if one factor is more or less than the error.
No. We don't do this. We just claim that one factor has a statistically significant effect on the outcome variable, and another factor does not have this significant effect. Well, in principle, I can check it. I guess there must be some version of Tukey test for this two-way layout. It might be disastrous in terms of calculations, but if there is some automatic method, why not? I can check it. Must be something.
Okay.
So you can do something like, well, if the person has different level of education, like bachelor, master, or like the candidates of science, and different gender, like 3 levels of one qualitative factor, 2 levels of another qualitative factor, and then you can compare, is there an effect on the salary, for example, of a gender, is there an effect of on a salary of an education level, and some interaction between them, or something like this. I don't know whether the person is villager or lives in town, and what is the number of family members in that in the family, and compare, and what is the effect on salary, let's say, of this person, something like that. So basically, once again, every time you have two qualitative, what does this mean, qualitative, right? So you can come up with several levels, and you cannot basically give them some numerical explanation. So different levels of factors, and you believe that they can influence the outcome variable, or there are some discrete levels of a factor, then this ANOVA might work well. On the exercise session, you will also have some examples of the practical applications of this. And now let me go to the plans. So, as I said, we established this method. We studied the Tukey's method, how to verify which sample differs from the others. And two-way layout helps us to incorporate two qualitative factors in the ANOVA analysis. So as I said, home assignment 6 is shifted and starts tomorrow, and is gonna be available till next Sunday, March 27. There is gonna be home assignment number 7 based on 2 sample hypothesis, and it starts on Monday. Then I will record you a short tutorial on ANOVA tests in Python, and I will try to post it on Monday, and then you will have a short quiz till the midnight of March. So as usual, 3-4 different functions that can be performed with the help of Python, and then some quiz where we need to repeat the same. One additional thing that I sent you a message yesterday, that you need to update 2 libraries. So you need to update stats, and you need to update you need to update SciPy, and you need to update stats models, if you have ever installed stats models. Why? Because well, this Tukey test that I used, I guess it appeared only in the latest release of SciPy. So before that release, Tukey test was not available there. So that's why I needed to update SciPy. But once you update it, there are some connections with other libraries. So therefore, stats models needed to be also updated. And probably you would also need to update NumPy. It happened to me, but somehow, like in the middle of calculations, so that's why I wasn't sure whether it's somehow related to those updates or not. So in any case, please read the message that I've sent you, do all the things, and if you have some troubles, immediately let me know. If your Python doesn't work for some reasons, immediately let me know, and we will try to solve this issue. because, as I said, this Tukey's method is available in the latest release, and I'm worried that this latest release has not been installed by you. And the very last thing, and the very important thing, I guess that everyone expects this: the midterm. I've heard that next week you are busy with some festival, whatever. So that's why let's put the midterm in the last day of March, March 31st, in the lecture time slot. So please make a note, 31st of March, to 2 weeks after today, we will have the midterm. What is gonna be there? I will give you one of the last topics. I mean, not one. So the midterm will include basically everything that we know about the hypothesis tests. 1 sample tests, 2 sample tests, and ANOVA. But those calculations are going to be based on some real data set. So you will get some Excel file, you will have some guidance, what kind of hypothesis you need to test, and well, you need to perform this test, you need to write down the conclusion of this test, and then you upload your solution, and I check this manually. So this midterm is going to be, of course, in the electronic format, but it's not going to be graded automatically. It's going to be graded manually. I will grade it, and I will check the whole solution. And for you, in order to, let's say, be ready how to deal with this, so in the next week, I will give you some example of the midterm, and I will probably provide you some solution of that midterm, so how you need to deal with this. It's gonna be something similar to what we did 2 weeks ago, when, if you remember, when I took that database on the Russian census in 2010, and we compared, what do we compare? We compared the fraction of males and females in Krasnoyarsk and Irkutsk region, right? So we compared the average age of Krasnoyarsk and Irkutsk population. So there is going to be something similar. So you will get the real data, you will have some question. So please test if some parameter equals to something, or please compare these two samples in terms of this. So therefore, you need to understand how to work with Python, definitely. You need to understand how to do the filtering that we did in the exercise session last week. And don't worry, I will provide you some guidelines, what exactly you need to refresh, or what exactly you need to study before the midterm.